Representation Theory of Finite Groups, Lecture 18, Problem Session. In this lecture, we will solve several problems related to the representation theory of the symmetric group. Problem 1. Compute the number of isomorphism classes of simple S9 modules. Solution. We know from our theoretical part that the pairwise non-isomorphic simple S9 modules are exactly the Specht modules S lambda, where lambda is a partition of 9. Therefore, in order to solve this problem, we just need to find the number of all different partitions of 9. And here is a list of all such partitions. So how can one construct this list? So we start with the partition 9 of 9. It has maximal part 9. Then let us list all partitions which have maximal part 8. So there is only one, 8 and 1. There are two partitions with maximal part 7, 7, 2 and 7, 1, 1. Then if the maximal part is 6, we have 6, 3, 6 to 1, 6, 1, 1, 1. For the maximal part 5, we have 5, 4, 5, 3, 1, 5, 2, 2, 5, 2, 1, 1, and 5, 1, 1, 1, 1. For the maximal part 4, we have 4, 4, 1, 4, 3, 2, 4, 3, 1, 1, 4, 2, 2, 1, 4, 2, 1, 1, 1, and 4, 1, 1, 1, 1, 1. For the maximal part 3, we have 3, 3, 3, 3, 3, 2, 1, 3, 3, 1, 1, 1, 3, 2, 2, 2, 3, 2, 2, 1, 1, 3, 2, 1, 1, 1, 1, 3, 1, 1, 1, 1, 1, 1, and that's it. And then for the maximal part 2, we have 2, 2, 2, 2, and 1, 2, 2, 2, 1, 1, 1, 2, 2, and 5 ones, 2, and 7 ones. And finally, we have one partition for which the maximal part is 1, namely 9 ones. So if we put all this together, we see that S9 has exactly 30 isomorphism classes of simple modules. Problem 2. Compute the action of the elementary transpositions of S5 in the standard basis of the Specht module S311. Solution. The elementary transpositions of S5 are the following 4 transpositions. So we can swap 1 and 2, we can swap 2 and 3, we can swap 3 and 4, and we can swap 4 and 5. From our theoretical part, we know that the standard basis of a Specht module is indexed by the standard Young tableaux of the shape which correspond to the partition for the Specht module. So in our case, we need standard Young tableaux of shape 3, 1, 1. So here are the 6 standard Young tableaux of shape 3, 1, 1. So the first one is 1 to 3, 4, and 5. Then 1 to 4, 3 and 5. 1 to 5, 3 and 4. 1, 3, 4, 2 and 5. 1, 3, 5, 2 and 4. And 1, 4, 5, 2 and 3. So now how can we compute the action of the elementary transpositions in the basis consisting of polytabloids for standard Young tableaux? For this we recall Young's natural representation, which says that if I and I plus 1 are neither in the same row nor in the same column of some standard Young tableau of shape lambda, then applying the transposition of I and I plus 1 to the polytabloid E indexed by this standard Young tableau, we get the polytabloid indexed by the standard Young tableau, which is obtained from T by swapping I and I plus 1. So in this case, swapping I and I plus 1 gives a standard Young tableau. So if I and I plus 1 are in the same column of some standard Young tableau, then applying this transposition to ET gives minus ET, because this transposition is in the column stabilizer of the tableau. And if I and I plus 1 are in the same row of the standard Young tableau, then this means that we should do this complicated procedure with Garnier elements. A general observation If I and I plus 1 are in the same row of some standard Young tableau, but there are no other elements in the corresponding columns, then the application of the Garnier procedure to the outcome of ET under the transposition of I and I plus 1 is simply ET, because the Garnier element is then trivial. It consists of the identity and then minus I plus 1. So this is a very easy case. And in our situation, for all elementary transpositions except 1, 2, the only Garnier element cases which appear are these trivial cases. Indeed, let us look at our standard Young tableau. So in the first tableau, we see that we have 2 and 3 in the same row. If we swap them, we will have exactly the case when 3 and 2 are row descent, but there are no other elements in their columns. The same is here for 3 and 4, and the same is here for 4 and 5. So it is only the elementary transposition 1, 2, which is in the first 3 cases, creates a non-trivial situation where we need to apply the Garnier element business to 4 elements. Okay, so using this, we can directly write down the action matrices for the elementary transpositions 4, 5 and 3, 4. So indeed, so 4, 5 here is in the same column, so we just put minus here. So here 4 and 5 are neither in the same column nor in the same row. So transposition of 4 and 5 swaps the second and the third basis vectors, and similarly it swaps the fourth and the fifth basis vectors. And here in the last case, 4, 5 are in the same row, but this is a trivial case where applying the Garnier procedure we just get the same basis vector. So the matrix of 4, 5 is minus 1 on the diagonal, then swap the second and the third basis vectors, then we swap the fourth and the fifth basis vectors, and the last basis vector is just an eigenvector with eigenvalue 1. So similarly for 3, 4, so here 3 and 4 swap the first and the second basis vectors. So here it's minus 1 because they're in the same column. Then here 3 and 4 are in the same row, but this is a trivial Garnier case where we just put 1. So it's an eigenvector with eigenvalue 1. And here again, swapping 3 and 4, swap the last 2 basis vectors. So the matrix is, we swap the first and the second basis vector, the third has diagonal element minus 1, the fourth has diagonal element 1, and we swap the last 2 basis vectors. Finally, for the elementary transposition 2, 3, in the first case we have this trivial Garnier, just 1 on the diagonal. Then if you swap 2 and 3 here, then the second basis vector will be mapped to the fourth basis vector, so they are swapped. Similarly, the third basis vector is swapped with the fifth basis vector. And in the last one, we just have minus 1 because they are in the same column. So the matrix for 2, 3 is 1 on the first diagonal, then we swap the second and the fourth basis vectors, and these ones we swap the third and the fifth basis vectors, and the last basis vector has minus 1. Okay, so the only complicated case is the computation for the elementary transposition 1, 2. So let us compute what happens if we apply 1, 2 to the polytabloid indexed by the tableau 1, 2, 3, 4, and 5. So applying 1, 2 to this polytabloid, we of course should just change 2 and 1, and this gives us the row descent 2, 1 in the first column. So now we can do the Garnier element business. So if we swap back, we will get it with coefficient 1. And then we can put, instead of this 1, we can put 4. And then the corresponding element is a 3 cycle. 1 goes to 4, 4 to 2, and 2 to 1. So 3 cycle is positive, the sign plus, but we move it to the other side of the equation, so we have the minus here. And finally here we can put 5. And then we will have the 4 cycle in the Garnier element, so the sign is minus, moving to the other side gives plus. And now we see that we have here the row descents 4, 3 and 5, 3. So these are these trivial row descents which can be dealt with by the trivial Garnier procedure. So the Garnier element which we used here is the identity minus the transposition of 1 and 2 plus the 3 cycle 1, 4, 2 and minus the 4 cycle 1, 5, 4, 2. So similarly, we can compute the application of the transposition of 1 and 2 to the polytabloid given by 1, 2, 4, 3, and 5. So if we apply directly, we will get the polytabloid for 2, 1, 4, 3, and 5. Exactly as before, we use a Garnier reduction to get the polytabloid for 1, 2, 4, 3, 5, minus the polytabloid for 1, 3, 4, 2, 5, plus the polytabloid for 1, 5, 4, 2, 3. So the first two are standard. The last one has this row descent, which is trivial to fix. And the Garnier element is similar as in the previous case. And the final Garnier computation is when we apply 1 and 2 to the polytabloid for 1, 2, 5, 3, 4. And then we will get the polytabloid for 2, 1, 5, 3, 4. And then using the same Garnier procedure as before, we will get that this is the polytabloid for 1, 2, 5, 3, 4, minus the polytabloid for 1, 3, 5, 2, 4, plus the polytabloid for 1, 4, 5, 2, 3. And we have a similar Garnier element as before. So now we can write down the matrix of the action of 1, 2. So we just computed the action of the transposition 1, 2 on the first three basis elements, so the corresponding columns just contain the coefficients which we got in this computation. In the last three basis elements, 1 and 2 are in the same column, so the application of 1, 2 just changes the sign, which gives us simply minus 1s on the diagonal for the last three columns. So this solves problem 2. Problem 3. Compute the character of the permutation module M4, 2. Solution. Denote by X the set of all two-element subsets of the set 1, 2, 3, 4, 5, 6. Note that X has 15 elements, so this is 6 times 5 divided by 2. And a 6 acts on X in the obvious way. So it acts by acting on each element of the subset, and of course this action is transitive. Given any two-element subset, we can move it to any other two-element subset by a bijective map. Observation: the stabilizer of the subset 5, 6 is the Young subgroup, which is obtained by the direct product of the symmetric group on 1, 2, 3, 4 and the symmetric group on 5 and 6. If we start from 5 and 6 in order to get it back, we can do whatever we wish with 1, 2, 3, and 4, and we can do whatever we wish with 5 and 6. So the stabilizer of 5, 6 is this Young subgroup, and in particular, since the action is transitive, it follows that the linearization of this action is isomorphic to the module which is obtained by induction from the stabilizer S lambda to the whole symmetric group S6 of the trivial module over the stabilizer. But we also know that this gives us exactly the permutation module M4, 2. We had this as a statement during the theoretic part. Recall from the general theory that for any sigma in S6, the value of the character of our linearization Cx on sigma equals the number of fixed points of sigma on X. Recall that the conjugacy classes in S6 are indexed by partitions of 6. Therefore, we can simply go case by case through all partitions of 6 and find the number of fixed points for some representative in the corresponding conjugacy class. And a fixed point for us is a two-element subset which is fixed by sigma. So let us start with the partition 6. So a representative is a long cycle. 1 goes to 2, to 3, to 4, to 5, to 6, and back. And there are no two-element subsets which are fixed by this partition. We always move one step in this cycle. No fixed points here. Next partition is 5, 1. The representative is a 5-cycle 1, 2, 3, 4, 5. Again, no fixed points. The next one is a partition 4, 2. And the representative is a product of the cycle 1, 2, 3, 4 and the cycle 5, 6. Here we have one fixed point, namely 5, 6. The next one is a partition 4, 1, 1. The representative is a 4-cycle 1, 2, 3, 4. And again we have one fixed point, namely 5, 6. The next partition is 3, 3. The representative is 1, 2, 3 times 4, 5, 6, the product of 2, 3 cycles. And there are no fixed points. The next partition is 3, 2, 1. A representative is the product of the cycle 1, 2, 3 and the cycle 4, 5. And we have one fixed point, namely 4, 5. The next partition is 3, 1, 1, 1. A representative is a 3-cycle 1, 2, 3. And this has 3 fixed points, namely the sets 4, 5, 4, 6, and 5, 6. The next partition is 2, 2, 2. The representative is the product of transpositions 1, 2, 3, 4, and 5, 6. And this has 3 fixed points, namely 1, 2, 3, 4, and 5, 6. The next partition is 2, 2, 1, 1. A representative is the product of 1, 2, and 3, 4. And there are 3 fixed points, 1, 2, 3, 4, and 5, 6. The next partition is 2, 1, 1, 1, 1. A representative is just a transposition 1, 2. And it has 7 fixed points for us, namely the subset 1, 2, but then any 2-element subset of the complement, which is 3, 4, 3, 5, 3, 6, 4, 5, 4, 6, and 5, 6. And finally, for the partition 1, 1, 1, 1, 1, 1, the only representative is the identity, and it fixes all 2-element subsets, so it has 15 fixed points. So we can now collect the answer. So the value of the character of our permutation module on a conjugacy class indexed by a partition is the following. So partition 6, the value is 0. Partition 5, 1, the value is 0. 4, 2, the value is 1. 4, 1, 1, the value is 1. 3, 3, the value is 0. 3, 2, 1, the value is 1. 3, 1, 1, 1, the value is 3. 2, 2, 2, the value is 3. 2, 2, 1, 1, the value is 3. And 2, 1, 1, 1, 1, the value is 7. And then 1, 1, 1, 1, 1, 1, the value is 15. Problem number 4. Decompose the permutation module M42 into a direct sum of Specht modules. Solution. We know that the only Specht modules which can appear in the decomposition of a permutation modules are those indexed by partitions which dominate the index of our permutation module. So we are only interested in Specht modules indexed by those partitions lambda which dominate 4, 2. There are only 3 partitions which dominate 4, 2, and these are 4, 2, 5, 1, and 6. Well, and then the answer, the multiplicity of the Specht module in the permutation module, is the number of semi-standard Young tableaux of shape, the index of the permutation module, and of the content, the index of the Specht module. So for shape 4, 2 and content 4, 2, there is only one tableau, 1, 1, 1, 1 in the first row and 2, 2 in the second row. For shape 5, 1 and content 4, 2, we can write 1, 1, 1, 1, 2 in the first row and 2 in the second row. For shape 6 and content 4, 2, we can write 1, 1, 1, 1, 2, 2 in the first row. So the answer, the permutation module M42, is a direct sum of one copy of the Specht module for 4, 2, plus one copy of the Specht module for 5, 1, plus one copy of the Specht module for 6. Problem 5. Compute the character of the Specht module S42. Solution. In the previous problem, we saw that the permutation module M42 decomposes as a direct sum of S42 and the Specht modules S51 and S6. Also, we have already computed the character of the permutation module M42. So, to compute the character of the Specht module S42, we need to compute the character of the complement of S42 in the permutation module M42. Namely, we need to compute the character of the direct sum of S51 and S6. But we know that S51 plus S6 is exactly the natural S6 module, which is also the permutation module M51. And we know that the character of the natural S6 module is given by the number of fixed points for each element acting on 1, 2, 3, 4, 5, 6. So if we write the cycle type of the element, it's just the exponent of 1 in that cycle type. So we can now collect all the characters we need. So the character of the permutation module M41 is just copied from the previous problems. The character of the natural S6 module is given by the exponent of 1 in the notation for the partition corresponding to the conjugacy class. So for the conjugacy class 6, the value is 0. For 5, 1, the value is 1 because there is only 1, 1. For 2, no 1s, 0. For 1, 1, we have 2 1s, so the value is 2. So 3, 3, 0. 3, 2, 1, the value is 1. 3, 1, 1, 1, the value is 3. This is the exponent of 1. 2, 2, 2, the value is 0. 2, 2, 1, 1, the value is 2, the exponent of 1. 2, 1, 1, 1, 1, the value is 4. And 1, 1, 1, 1, 1, 1, the value is 6. So in order to get the character of the Specht module, we simply need to subtract the character of the natural module from the character of the permutation module. So the outcome is the following character. So the character of the Specht module evaluated in the conjugacy class 6 is 0, because it's 0 minus 0. For 5, 1, it's 0 minus 1, minus 1. For 4, 2, it's 1 minus 0, which is 1. For 1, 1, 1 minus 2, minus 1. 3, 3, 0 minus 0 is 0. 3, 2, 1, 1 minus 1, 0. 3, 1, 1, 1, 3 minus 3, 0. 2, 2, 2, 3 minus 0, 3. 2, 2, 1, 1, 3 minus 2, this is 1. 2, 1, 1, 1, 1, 7 minus 4, which is 3. And 1, 1, 1, 1, 1, 1, it's 15 minus 6, which is 9. Problem 6. Compute the number of standard Young tableaux for the partition n minus k, 1 to the power k, for any k between 1 and n, not including 1 and n. So if you write the picture, then we see that we are talking about standard Young tableaux of the following hook shape, when we have n minus k elements in the first row, and then k additional rows consisting of one element each. And we can observe that the box 1 must be in the top left corner. In the remaining parts, we have n minus k minus 1 elements in the first row, and then k elements in the first column. So if we arbitrarily choose these n minus k minus 1 elements out of 2, 3, 4, and so on up to n, then we can place these elements uniquely in the first row in an increasing order. What is left is exactly k elements out of these, and this can be placed uniquely in the first column in the increasing order. And the outcome will be a standard Young tableau of our shape. And clearly any standard Young tableau of the shape can be obtained in this way. So the answer, the number of standard Young tableaux of shape n minus k, 1 to the power k, is equal to the binomial coefficient n minus 1, choose n minus k minus 1. Alternatively, the same is n minus 1, choose k. Problem 7. Determine the multiplicity of the Specht module S3 to 2 in the restriction from S10 to S7 of the Specht module S43 to 1. This is a question about restriction, so we need to apply our branching rule. And let's compute the restriction step by step. Let us first restrict to S9. So if we restrict S43 to 1 to S9, we get a direct sum of Specht modules indexed by partitions obtained from 4, 3 to 1 by removing a removable node. So if we remove the removable node from the first row, we get 3, 3 to 1. If we remove the removable node from the second row, we get 4, 2 to 1. If we remove the removable node from the third row, we get 4, 3, 1, 1. If we remove the removable node from the fourth row, we get 4, 3, 2. So now we can apply the branching rule to compute the restriction of each of these 4 components to S8. So S3, 3 to 1 restricted to S8 gives us S3, 2 to 1 plus S3, 3, 1, 1 plus S3, 3, 2. So the Specht module for 4, 2, 2, 1 restricted to S8 gives us S3, 2, 2, 1 plus S4, 2, 1, 1 plus S4, 2, 2. So the Specht module for 4, 3, 1, 1 restricted to S8 gives S3, 3, 1, 1 plus S4, 2, 1, 1 plus S4, 3, 1. And finally, the Specht module for 4, 3, 2 restricted to S8 gives S3, 3, 2 plus S4, 2, 2 plus S4, 3, 1. So if we collect this together, then the restriction of the original Specht module S4, 3, 2, 1 to S8 is a direct sum of the following Specht modules with the following multiplicity. So S3, 2, 2, 1 is with multiplicity 2, then we have S3, 3, 1, 1 with multiplicity 2, and the same multiplicity 2 we have also for S3, 3, 2, S4, 2, 1, 1, S4, 2, 2, and S4, 3, 1. So we need to compute the multiplicity of S3, 2, 2. So S3, 2, 2 appears with multiplicity 1 in the restriction to S7 of the following Specht S8 modules from our list. So we can restrict S3, 2 to 1. So if we delete the removable node in the last row, we get exactly 3 to 2. So we can start with S3, 3, 2, delete the removable node in the second row to get S3 to 2, or we can start with S4 to 2, delete the removable node in the first row and get S3 to 2. So if we now put all this together, so each of them appears with multiplicity 2, this guy appears in the restriction of each of them with multiplicity 1. So if we combine all this information together, we get that the multiplicity of S3 to 2 in the restriction from S10 to S7 of S4, 3 to 2 is 2 plus 2 plus 2, which is equal to 6. And finally, problem 8. Write the polytabloid for the Young tableau 6, 5, 4, 3 to 1 as a linear combination of the standard basis elements in the Specht module S2 to 2. Solution. So let us first order the columns in this Young tableau. In order to order the columns in this tableau, we need to swap 2 and 6 and 1 and 5. So our element is obtained from the polytabloid for 2, 1, 4, 3, 6, 5 by applying the product of the transpositions 2, 6 and 1, 5. So this product is an even element, and so the outcome will be the polytabloid 2, 1, 4, 3, 6, 5. So what we really need to do, we need to compute the coefficients of the decomposition of this polytabloid in the standard basis of our Specht module. So now our columns are ordered, so we need to eliminate all row descents. We start with the row descent 6, 5 and need to start as low as possible with maximal numbers. So we start with the row descent 6, 5 and we can eliminate it using the Garnier element identity minus the transposition of 5, 6 plus the 3 cycles 3, 5, 6 minus the 4 cycle 1, 3, 5, 6. And in this way we write our polytabloid as a linear combination of the polytabloid for 2, 1, 4, 3, 5, 6 minus the polytabloid for 2, 1, 4, 5, 3, 6 plus the polytabloid for 2, 3, 4, 5, 1, 6. Again, we can order the columns in the two last elements to write our polytabloid for 2, 1, 4, 3, and 6, 5 as the polytabloid for 2, 1, 4, 3, and 5, 6 plus the polytabloid for 2, 1, 3, 5, and 4, 6. This is because we swap here 3 and 4. And then plus the polytabloid for 1, 3, 2, 5, and 4, 6. Because here we apply the 3 cycle, which moves 2 steps up. And now we can note that the last tableau is now standard. 1, 3, 2, 5, 4, 6 is a standard Young tableau. So this one is done. And now we need to concentrate on the first two summons. So let us compute the polytabloid for 2, 1, 3, 5, 4, 6. So we need to eliminate the row descent to 1 in the first column, and we use the Garnier element identity minus 1, 2 plus 1, 3, 2 minus 1, 4, 3, 2. And in this way, we write our polytabloid as the linear combination of the polytabloid for 1, 2, 3, 5, 4, 6 minus the polytabloid for 1, 3, 2, 5, 4, 6 plus the polytabloid for 1, 4, 2, 5, 3, 6. And here, all polytabloids which appear on the right-hand side correspond to standard Young tableaus. So this is done. And next, we need to deal with the summon the polytabloid for 2, 1, 4, 3, 5, 6. Here we need to eliminate the row descent for 3, so which involves elements 1, 3, 4, and 5. So it will be a row descent of S4 modulo S2 times S2. So the corresponding Garnier element will be identity minus 3, 4 plus 3, 5, 4 plus 1, 3, 4 minus 1, 3, 5, 4 and plus the product of 1, 4 and 3, 5. And we write our polytabloid as a linear combination of the polytabloid for 2, 1, 3, 4, 5, 6 minus the polytabloid for 2, 1, 3, 5, 4, 6 minus the polytabloid for 2, 3, 1, 4, 5, 6 plus the polytabloid for 2, 3, 1, 5, 4, 6 and minus the polytabloid for 2, 4, 1, 5 and 3, 6. Again, we can order the columns, and so we get the polytabloid for 2, 1, 3, 4, 5, 6 minus polytabloid for 2, 1, 3, 5, 4, 6 and then plus, so this plus because here we have to swap 1 and 2, right? So we get the plus the polytabloid for 1, 3, 2, 4, 5, 6, and then minus the polytabloid for 1, 3, 2, 5, 4, 6, plus the polytabloid for 1, 4, 2, 5, 3, 6. And the 3 last polytabloids now correspond to standard Young tableaus. So again, we have 2 polytabloids to deal with. For 2, 1, 3, 4, 5, 6, we eliminate the descent to 1 using, as usual, the Garnier element identity minus 1, 2 plus 1, 3, 2 minus 1, 5, 3, 2. So we get that this polytabloid is a linear combination of the polytabloid for 1, 2, 3, 4, 5, 6 minus the polytabloid for 1, 3, 2, 4, 5, 6 plus the polytabloid for 1, 5, 2, 4, 3, 6. And we can order the columns. There is this 5, 4 problem in the last case, which gives us the sign minus, and we get our linear combination, and everything on the right-hand side is now a standard Young tableau. And finally, we need to deal with the polytabloid for 2, 1, 3, 5, 4, 6. We eliminate the descent to 1 using the same Garnier element as usual. So we get the polytabloid for 1, 2, 3, 5, 4, 6 minus the polytabloid for 1, 3, 2, 5, 4, 6 plus the polytabloid for 1, 4, 2, 5, 3, 6. And everything on the right-hand side is now standard. Now we can combine together all these formulas to get that the polytabloid which we wanted to compute is the linear combination of several expressions which we got during the computation, and when we compute everything involved here, we just get the polytabloid for 1, 2, 3, 4, 5, 6. And this completes the solution. So here are some problems and questions. Question 1. Compute the action of the elementary transpositions of S5 in the standard basis of S221. Question 2. Decompose M222 into a direct sum of Specht modules. Question 3. Compute the character of the permutation module M33. Question 4. Compute the character of the Specht module S33. And question 5. Write the polytabloid for 654 and 321 as a linear combination of the standard basis elements in the Specht module for 3,3. Thank you very much and see you next time.